Now, what I want to do is to explain why Maxwell's demon today is realized cannot exist because of a fundamental reason related to computation. And this will inform us a great deal in our journey through quantum computation, because we want to be aware of these limits of physics on computation as we try to realize a new model of computation. So the way I will describe this is with a beautiful construction called Szilard's engine, or Szilard. From 1929. Look at the span of years between these discussions. There are 8 steps in Szilard's engine. So I will describe each one of them, but they will be very simple, easy steps. It may take me a little bit to draw each one of them, so bear with me. The basic idea is this configuration, which will be the core engine. And this core engine will, again, be a cylinder of gas. I'm drawing its cross-section, or think of this as a 2-dimensional idealization of it. There will be a wall that can come down through a small hole in a partition. This is supposed to be the same size on both sides. And imagine that there's just one gas molecule rumbling around, for sake of simplicity, inside this idealized vacuum chamber. All right. In addition to this, I'm going to explicitly add one thing here which might seem a little odd. It's a piece of scratch paper. It's a little memory. And we'll see what that piece of memory is used for in just a moment. So instead of having a Maxwell demon sitting inside a populated gas chamber, we'll start with just this. And this stage is called the initialization stage. In the second stage, which we'll call wall lowered, we have the same configuration. These are pistons that later we'll see can slide in and out. The reason there are 2 of them is because we're going to lower this wall in the middle at some random time. And we don't know whether the molecule is going to be on the right-hand side or the left-hand side at that time. So for sake of concreteness, let's imagine that at the moment we lower the wall, the molecule just happens to be on the right-hand side of the cylinder. All right? It might have been on the left-hand side. It's probably equally probable given a normal distribution or Maxwell-Boltzmann distribution. OK. In this third stage, remember our scratch pad is still in this configuration. We're going to measure where the molecule is. So imagine this is just like Maxwell's demon looking with his or her eyes at a gas molecule. Now we're just going to look at one thing. Is the molecule on the right-hand side or on the left-hand side of this double cylinder configuration? All right. So here we go. We don't change anything about the cylinder or its 2 pistons. But we do observe this molecule as it's careening around and bouncing off the walls. And we see that it's on the right-hand side. And because it's on the right-hand side, we'll write down an R on our scratch pad memory. Okay? If it had been on the left-hand side, I would be doing something almost identical in the next few steps. The next step is the one which makes a difference with respect to whether you knew it was on the left or on the right. Given that the molecule is the only molecule in this cylinder, how hard is it for me to move this piston in on the left-hand side? Yes, please.
It takes 0 effort.
It takes 0 effort because nothing is pushing back on it. Maybe there's just a vacuum over here. There's vacuum everywhere in this world. Okay, so the only thing that's pushing something around is this one solitary molecule kicking around. Okay? In fact, as it bounces around, it's probably pushing against this piston too, but we're holding it still, so nothing's happening. But the key is, as you just said, it costs us no energy and effort to move this one piston on the left in because there's no molecule over there. And we can do that because we know it's on the right-hand side. So we just compress on this left-hand side. That's step 4. Step 5. Now we raise the wall. So the wall goes up. Now we have the left piston over here and the right piston over here. And we have this molecule that's still bouncing around, careening around over here. And in this step, we have the molecule running around at some random point on the right-hand side of this double cylinder. And because it's bouncing around, in this next step, which I'll call expand, the wall stays up. What happens? Well, this molecule at some point will randomly have a trajectory which hits this wall and bounces off. And when it hits this wall, this movable wall as a piston, the piston moves backward like this. Okay, these are very, very light pistons, and this is a really, really kind of momentous molecule that's moving around. Okay, and so it goes and goes bing, and it moves the piston, and goes bing, and the piston moves out further. You know, you might have to wait a while. But everything in the service of a PhD thesis, right? So you can guess what the next step is. We're at stage 6. We're almost done. Stage 7, as we let this ping back and forth, eventually this left piston is going to move all the way back to its initial state. So we can say that we are resetting the position. And this resets the position of the 2 pistons. We have the wall out. The pistons will come back into their initial state over here. Let me not forget our little scratch pad over here. And from a mechanical standpoint, we're nearly back to the initial state. What do I need to do? What last thing do I need to do to get back to the very initial state of this system? Somebody else. I heard it, yeah, yellow shirt? Clear the memory. Clear the memory, yeah. What's so hard about that? Don't you do that all the time? What's so hard about clearing the memory? I'm sure you've experienced this before. You know, it's awfully hard to forget some things. But this is a single bit. What could be so hard about forgetting a single bit of information? Well, OK, that's awfully hard to forget sometimes, too. Thoughts, answers? Anyone? Except the 2 who have answered most of the questions? How about a student who's wearing a nice Chad Rigetti shirt?
It takes work.
Why does it take work? It's non-random. And so, in fact, if this is to go back to an empty state afterwards, then you had some random piece of information here which you're putting back into a non-random state. So somehow you had to get rid of randomness. It's that getting rid of randomness, because this could have been an L just as equally likely as ended up being an R here. Getting rid of randomness is hard. Getting rid of something you know is in some state is not so hard. And this is an important principle we'll come back to as we look at reversible circuits in a moment. Yes, please.
Isn't the molecule moving slower than it was at the beginning?
Yes, it is. So I'll draw my arrow a little shorter. Thank you. OK. So we are now modulo the molecule moving slower back at the initial state. So this is done by erasing the memory. And lo and behold, it is exactly that cost that had been neglected in Maxwell's demon scenario. He didn't actually think about the cost of the demon having to forget its last piece of information.
Why aren't we taking into account the movement of the wall?
Right. Because I'm really good about building my wall on rollers here, see, not just hinges. And so compared with the cost of everything else, it's a very small amount of energy. It's also reversible. Like imagine that the wall was heavy, so I just let it drop, and then I harvest that energy from the dropping, and then I bring it back up. So you can imagine I have a series of weights and cantilevers to just move the energy of the position of the wall between its two configurations. Okay, so it can be made very, very small. Of course, I've only considered a single molecule, which is a very small amount of energy here. But maybe this is a very, very fast-moving molecule. Okay, good question.
And then does it lose energy? So what if the energy that it loses as it moves is harnessed and is used to erase the memory?
Yes, so I could use the energy harvested from this piston to erase this. But eventually, I'm going to run out of steam. So this is no longer a continuously operating engine like I might have had in another scenario. So I can harvest energy as long as I can quantify net energy, as long as I can quantify the energy that it takes to erase that bit. That's what I would like to claim in just a moment after I answered these two questions. Yes, please. Blue shirt.
Why would you necessarily run out of energy? Why would you necessarily run out of energy? The molecule's not going to stop moving entirely.
It is true that the molecule's energy may eventually be lower than, say, the friction of the piston, something like that. So these now start to come into practical bounds. But in computer science, we like to think about asymptotics and what you could do in an idealized situation. And the main point of this discussion here is something that was picked up on, and I'll describe that in just a moment. Question, please.
Why is it important to start with an empty memory? Can't you just say it's in some state and then I just write it to a 0 or a 1 and
Yes.
and then that way I don't have to clear it again, really?
Yeah, the question is, why is it important to start with an empty state of the memory? Why couldn't I just, for example, erase it at the beginning? You could do that. It would be just a transient and another stage I could add. And effectively, that would be making step number 8 equal to the first step instead. So I claim the rest of the procedure would just follow along. Okay. So the connection between this and computation was really made by this. Rolf Landauer in 1961. Rolf Landauer, a very accomplished and famous physicist from IBM in the heydays of IBM's impact on the foundations of computer science, formulated this beautiful observation that an n-bit register, notice now that we're talking about the scale of some problems, so we're now going to go to an asymptotic limit where n is some meaningfully large number. And we know that this register has 2 to the n configurations. So it's like n of these boxes of scratch pad over here. And clearing this register to some standard state is like as we have just seen, compressing a gas in the sense that all the configurations, no matter what value you have in that n-bit register, must go to some definite final state, whether it be all zeros or all ones or whatever else you decide. You lose the randomness that you had. And his observation is that this causes a flow of entropy. And I realize I haven't described entropy for you, and I hope you can inherit some of that understanding from your own understanding of thermodynamics. But the point is that this entropy that was the randomness of this register must go to the environment. And this is due to, I said, talk about thermodynamics. This is due to the second law of thermo. Because entropy is conserved, and that entropy must move somewhere, and where it goes is into the environment. And that means that the erasure must cost some energy, as many of you observed. And I want to quantify that again now using the laws of thermodynamics. And as Rolf Lander points out, it's kT log base e of 2, because there are only two possibilities for each bit, and this is per bit. And this is of energy. And this is due to the well-known result that the heat pumped is equal to the temperature at which you're pumping it times the change in entropy. So the log 2 is just the measure of entropy, the randomness of a bit. And then the kT is the energy that comes from the laws of thermodynamics. And this K is Boltzmann's constant. And it's a scale that's used to inherit the idea of Avogadro's number in a mole. Yes, please.
So this question has already been sort of asked in a different form, but so what if we used a different definition of erasure? As in instead of reducing everything to one final state, sort of just re-rolling the dice and randomizing everything.
OK.
Does that cost less energy? Or?
OK, so the question is, what if we use a different notion of erasure? Maybe we'll re-roll the dice and use a different configuration. But you see, there's entropy in this bit here. It was either left or right. That entropy had to go somewhere. And there's no way around that. So you could take a little bit less entropy, make it less random. But then you'll get less energy harvested. And so it all still comes back to you as this cost. Other questions? Okay, so this is beautiful. This result is known as the exorcism of Maxwell's demon. And when I learned about this, I was like, wow. This is a really beautiful connection between fundamental physics and computation. And so you might say, well, how much does it actually impact computation that we use around ourselves today in our daily work? And so the answer is modern computers actually consume something like 500 kT log 2 joules per bit erased. It might not seem like very much, but you erase a lot of bits all the time in a modern like Intel processor. Now, if you were a DNA computer, that can work in principle at 1.5 times 10 to the minus 19 joules per operation, which is and corresponds to 2 adenosine triphosphate phosphorylations. So ADP is exchanging, ATP is exchanging. And this is approximately 120 kT log 2. So it's not that far away from what biological systems, maybe a factor of 4 or something. So it's very respectable. Can we do better? Why do we need to expend energy like this? We've had a persistent level of questioning about the need to do erasure. So I want to challenge you. Could we build a computer that doesn't need to erase? If we could build a computer that did not need to erase information, maybe it would not need to dissipate energy to do the computation. And this brings us to the third topic of today's lecture, the fact that you could actually do that in principle, and that's the idea and the story of reversible computing.